So happy Monday, part 2. See is the attendance register. Any questions or anything before we start? Okay, if there are any questions or comments, just feel free to interrupt or raise your hand at any time. So today's lecture is a little bit non-trivial, kind of difficult to understand. So in the volume visualization topics, the first, big algorithm was marching cubes, and that was object order algorithm, indirect, and it produces surfaces, which is a set of triangles, and certainty is implied. Then the next algorithm, which was earlier, was this ray casting algorithm, which is a direct volume visualization image order. But the first version of that algorithm, the version we talked about today, was not necessarily optimized for speed. So now we're going to talk about another volume visualization method, direct volume visualization, that is more optimized for speed. So it's like an accelerated version of what we talked about earlier today, and it's tricky. And it's called the shear-warp factorization. So this is a hybrid, so-called hybrid of image order and object order rendering. Does anybody know what that word hybrid means? Anybody know what the word hybrid means? Probably there's somebody in this room that knows what that word means.
Is it like a combination?
A combination of two things, that's right. Name?
Ferris.
Ferris, exactly. Thank you, Ferris. So this is a combination of image order and object order rendering. This is an overview of what it looks like. It involves 3 major steps, and it relies on something called a permutation matrix for coordinate system transformation. So here is our original data set organized on a series of slices, and here is our image plane, and we are looking through the image plane at the volume. And these are rays that are being casted into the volume for sampling purposes, just like we saw earlier today. But they're cast at an angle. And the idea is to, in some ways, rotate the view so that it's orthogonal to these slices, therefore making the rays orthogonal to the slices themselves, and do our compositing along these rays, which are orthogonal to the slices, making the compositing stage and the sampling stage very fast. But if we want this angle, if we want to look at the volume from an angle, we can't just rotate our viewpoint. What we do is we shear the volume we do our sampling and then unshear the results or warp the results back. That's the way I see it. So there's a transformation that shears the volume, in other words, slants it to the side, and then transforms it back to unshear it in the image space, or the unwarp, so to speak. And the idea is that the rays, instead of the rays sampling the volume at an angle, which produces that extra computational overhead because of interpolation, we sample the volume on a 1-to-1 ratio of voxels to pixels, and that makes it much faster. That's the overview. And the next slides are talking about this in more detail. So here's another look. Step 1 of the algorithm is called the shear step. And that's when the data is organized on slices in a volume. And normally those slices are stacked on top of each other in a cube. But you can imagine sort of leaning the cube in different directions, right? And that's called shearing the cube, or shearing the slices. So the first step is shearing, or translating those slices in the X and Y position. And that's the next step is called a projection step, and that's the compositing, the 1-to-1 pixel to voxel, to create a 1-to-1 voxel to pixel ratio. So the shear in this example is along X and Y in this direction. This is a so-called voxel scan line. So we're sampling the volume along this scan line from left to right. And we're doing and then we do a projection and compositing in the next step. And to compensate for this initial shear warp, which distorts the volume, it distorts what you're looking at, there's an unshear stage, which in this case is called warp. So warp and resample. So this is a picture of a voxel slice, right? That's one of these slices. And when you composite, when you shear them, the result looks distorted. It looks warped, right? Because you're not looking at it from the same angle anymore that you were to start with. And look, after you composite the result, it looks strange, right? That's an intermediate result. So imagine compositing a stack of these and getting this warped result. That's an intermediate result, and then it has to be warped back to its original. And that's what the final output looks like when it's unsheared or transformed back to the original viewpoint. So the shear happens in object space. The composite happens in object and image space, and then the warp happens in image space. So that's why it's called a hybrid image and object order algorithm. So let's look at that further. Remember this slide. This is kind of the crux of the whole thing. This slide is the crux, because when we cast a ray into volume data, it is computationally expensive to sample that volume data. And this is just the 2D version. If we intersect the volume along an edge, we do a linear interpolation, which in this 2D case, it's one interpolation. In the 3D case, does anybody remember how many interpolations that is?
7.
Almost. It's a little bit of a trick question. Along an edge, it's only 3, but it's 7 in the interior. So it's normally 7. That's normally correct. That's an expensive operation, 7 interpolations. Here's 7, 7, 7. In this one, this is nearest neighbor interpolation, so it's always just 1, and it's a simple operation, but it's inaccurate. Here, we have always, well, in this 2D case, it's 1 linear interpolation along the edges, but the sampling is non-uniform. In this case, it would always be 3. If we extended this to 3D, it would always be 3 interpolations. But what if we could transform these rays in such a way that they were orthogonal to the volume? So they're pointing straight from left to right. So instead of going at an angle or intersecting the volume at an angle, they were going straight from left to right. You'd get a nice sampling configuration because you'd have uniform sampling and the minimal interpolation. So could you imagine in your head shifting all these slices down proportionally so that the rays go from straight from left to right? You'd actually have to take this, imagine this is the center of rotation, and rotate all of the slices down, and that would shear them to get the ray straight, if that makes any sense. So in order to sample this voxel, we would have to shift it down 2 units to get this ray to go from left to right. And this voxel would have to get shifted down 2 units as well, but this one is a little bit more than 2 units. Like this one would get shifted down the most. This one would get shifted down the second most, because I'm tight. And this one would get shifted down the third most. Does everybody see that? Here we only have to shift 1 unit down, 1 unit down, half of a unit down, half of a unit down, like a fraction of a unit down, and this one we wouldn't have to shift at all. That's the shear. That's the shear part of the algorithm. So we have a stack of slices. We shear them in both the X and Y directions. Then we composite and project along the Z axis, and then finally a warp operation. That's like the unshear, and that's done in image space. And why is it faster than the traditional ray casting? There are a few reasons, but one is the compositing. The compositing is faster because the rays are always orthogonal to the slices. Does everybody know that word, orthogonal? Anybody want to say what orthogonal means? Name?
It's a 90-degree angle.
That's right, that's right. What's your name?
Sam.
Sam. Awesome. At a 90-degree angle. So like that, orthogonal. How about this one, Sam? Do you know the complement or the opposite of orthogonal?
Diagonal?
Close. Anybody know the opposite or the complement of orthogonal? So right angle. I thought the first question was trickier. That's perpendicular.
What is the angle? Or are we looking at just about the angle?
Well, like the opposite of perpendicular or orthogonal. Is there an opposite or a dual? I thought the second question was easier than the first one, actually, but I could be wrong. Is it Hannah?
Yeah.
What would you say, Hannah?
Parallel.
Parallel, exactly. So it's the opposite of parallel in a way. So, what was I saying? So that's one of the reasons it's faster is because the compositing is accelerated by this orthogonal configuration. And we're also going to use an acceleration technique called run length encoding for sampling the data. And that's going to be on the next slide, I believe. So this is kind of a pseudocode summary, and this is with a focus on the run length encoding for accelerating. It's accelerating the composition stage of the shear-warp factorization. Anybody heard of run length encoding before? Anybody want to try to say like where you've heard it before?
Data compression.
Exactly. It's like the world's simplest data compression technique. So instead of it's usually used in which context? And where do you usually hear about it? You've heard of it before, but it's usually not used in volume visualization. The attendance register somewhere? Everybody signed that? Anyone feeling brave? You've heard of run length encoding before. In what context?
I'll take a guess. Is it repeating patterns?
Repeating patterns?
So like bits?
Yep, repeating bits in any particular application. Well, the first time I heard about it, it was in the context of networking. If you want to transmit an image from point A to point B, you have to transmit the RGB values of every pixel, right? And the alpha values. But if you had a red image, imagine you just had a red image of 1 million pixels of red. Does it make sense to transmit like the number that represents red 1 million times? That's not very efficient. You would rather just transmit the value of red times 1 million, like the length, the run length of the number of reds, you know, rather than transmitting red 1 million times. So it's usually used in this context of networks and image compression, because you're trying to transmit images over a network, right? So, and there are all these different compression techniques, right? JPEG, MPEG for videos, GIF, you know, and lots of different kinds of image compression techniques. So that's where you usually hear about it. So we're taking the same content, the same idea, and then using it in volume visualization. So select the data set and apply the shear. That's this step, right, when we shift these slices. Now, it says for all scan lines do. There's an example of a scan line from left to right. Voxel scan line. For all scan lines, do the following. So this is a scan line on a slice of data. And it says skip transparent voxels run. So here is, because we have, these are voxels and these are pixels. Remember, we have this, we've set up this 1-to-1 ratio of voxels to pixels. That's one of the acceleration techniques. That's why we shear the volume in the first place, is to set up that 1-to-1 ratio. And that's why we can have a row of voxels and a row of pixels lining up 1-to-1 in this image. That's what we see there. Without the shear, that wouldn't be possible. So here we're skipping a row or a run, 1, 2, 3, 4, 5, of transparent voxels. That's run length encoding in object space, because we can skip a bunch of transparent voxels. Here we have a non-transparent or an opaque voxel, and it gets composited. In other words, its color and opacity are projected onto the image plane. That's called compositing. When you add the color and the transparency to the pixel, that's called compositing. Now, I don't know if anybody can remember, but in the last lecture, we talked about front to back ray casting. And when the ray reaches the maximum opacity, we can terminate it. We no longer have to sample the volume because we can't see anything behind it. That is what we're seeing now. So we're seeing 3 pixels at maximum opacity, and therefore we can skip the compositing stage because the colors and opacities don't change when we've reached maximum opacity. So we have a run of voxels, we skip, we do a composite stage, we have a run of opaque pixels that we can skip. So we don't have to do the compositing for these 3. Here we have an opaque pixel and an opaque voxel, or a semi-transparent voxel, another semi-transparent voxel. And these 2 pixels are not opaque, so we do the compositing, like the standard compositing, adding colors from front to back. Colors and opacities. Here we have a run of 3 transparent voxels, so we can skip them. Here we have a run of 2 opaque pixels, so we can skip the compositing phase. And here we have 3 voxels that are semi-transparent, and their corresponding pixels are not fully opaque. So we perform the compositing from front to back as usual. So there are 2 accelerations happening there. One of them is in voxel space, skipping runs or rows, or, well, in this case, it's skipping rows of transparent voxels. And then in the image space, we're skipping runs of opaque pixels to reduce that expensive compositing phase or aspect of the algorithm. So that is the acceleration, part of the acceleration, using run-length encoding to accelerate the compositing part. And that's only possible because of the shear, that first operation that shifts the data to make it equivalent of tangent rays to the viewpoint. I'm sorry, orthogonal rays to the viewpoint. So that's a tricky slide, that one. And that's a tricky aspect. You might have to review that to get it to, if it didn't click the first time, you might have to look at it again. And the warp is the unshear, and that happens in image space. Did that make a little bit of sense? Maybe just a little bit, hopefully, to everybody. Now, there are two kinds of projections. One's called perspective projection. Anybody know what the other one is called? Anybody, computer graphics enthusiasts here? This is really a graphics question, in my opinion. Perspective projection and another one. Anybody remember graphics, different projections? Maybe that's too deep in the recesses of your brains to pull out. The other one's called parallel projection. Does that ring a bell to anybody? Parallel and perspective projection. Parallel projection is when you have an image and all the values are computed such that the rays are all parallel with each other. Right, so you're shooting rays that are parallel with one another to get your view. And that's kind of the default view for computer graphics and visualization because it's simple and it accelerates the computation. But that's not how our eyes work. That's not really how our eyes work. So when I look at something, I have you can think of like two rays coming from my eyes. That's also a simplification. But if I'm looking straight at an object, the two rays that I cast from my eyes are not exactly parallel. They meet at a point. They're not exactly parallel. I'm exaggerating now. But so if we want to get an image that's more realistic, we have to use perspective projection. That's what this is. So the rays are no longer parallel to each other. So to incorporate a perspective projection, we incorporate a shear and scale into the shear phase. So here, like those are that's our eye, so to speak, one of our eyes. And we cast rays from our eyes, but they're no longer parallel. Right? In this image, they're parallel. This is the default. So we compute pixel colors and opacities based on parallel rays. That's parallel projection. And it's faster. But if we want it to be a little bit more realistic, we have to use perspective projection. The rays are no longer parallel. So the shear does two things. It translates the slices and scales them down and makes them smaller, shrinks them the further away they are from the viewpoint. Because that's what happens in real life, or that's what happens with your vision. The further away an object is in reality, the closer the two rays are to being parallel. So if you have two rays being parallel, makes objects appear further away than they actually are. So has anybody ever seen in there, like your car's rear view mirror, do you have these things that say, like these little stickers that say objects may appear closer than they, or objects may be closer than they appear? Has anybody ever seen that sticker on their car before, in their rear view mirror? Anybody ever seen that? I've seen that many times. Nobody else has ever seen that? One other person? That's the reason. Now you know the reason. Well, if nobody's ever seen it, then it's irrelevant. So but it's very common in the US. If you're driving around in the US, I've seen that many, many times. And that's what this looks like. So there's a shear and there's a scale applied to every slice. So that slices further away get smaller. So the advantages of the shear-warp factorization is that it's fast, it's easy, and perspective projection can be incorporated. The disadvantages is that this is also an advantage if you want to say it. Reconstruction is only bilinear or within slices. That means interpolation, by the way. Interpolation is bilinear, so it could be construed as less accurate as opposed to trilinear. And this voxel to pixel ratio is 1:1, which can lead to aliasing artifacts if you zoom in. But if you zoom into an object and you insist that this ratio is 1:1, then the voxels are going to spread out, and your samples are going to spread out, your sampling, and therefore you can run into aliasing artifacts. These are some images from the shear-warp factorization algorithm, so you can get images that look like that, high-quality images. Here's a comparison of traditional raycasting with the shear-warp algorithm. So here, raycasting looks to me a little bit more crisp, like the sampling rate is a little bit higher. Like the shading looks a little bit better here. Right? And if we zoom in, right, there's a little bit of blur in the shear-warp algorithm. Right? And here we see a little bit of blur too. But it's much faster. So if we're zoomed out, the images are very comparable. Here, when we zoom in, we can start to notice differences. And if that was difficult to understand, there's a paper you can read on Blackboard that explains it in more detail. It may be a little bit slower. And I just thought I would show a video too of what volume visualization can look like, and not just slides. So this is sort of a state-of-the-art or like very fast volume visualization using different acceleration techniques, not only the shear-warp factorization. But this is like a nice demo of state-of-the-art volume visualization rather than looking at just some slides, to see it in action. This is what you can create on your software when you download different pieces of software and you start to visualize the volume data, like Betty and Sally, for example, or the visible human, or a walnut, for example, whatever sample data sets you are looking at. So you can visualize this in real time now, not at slow frame rates like back in the days when those papers are published. And these are using different transfer functions at the same time. Right? For example, maybe using maximum intensity projection for one segment of the volume, and using X-ray, for example, for the bones. So it's combining multiple transfer functions at the same time. Remember, we had a lecture on focus and context for information. It was focused on information visualization. Well, the same ideas can be applied to volume visualization, focus and context. So this is focus and context volume visualization. And these are all, you can see, parts of the body, the human body. because medical visualization is one of the central applications for volume visualization. That's a kind of focus and context style rendering with the brain soft tissue as the focus. Here is an example of direct volume rendering, right, using different transfer functions, different shading. And that's what happens, that's what it looks like when the user interacts with the volume, right? They rotate it. There are two subsets of the volume there, right? One for bone, one for the surrounding skin. This is a style that enhances the silhouettes or the edges of the bone structure. Here's summation, a sample of summation transfer function. Another example of maximum intensity projection. So this is fusing different transfer functions together, right? One for the skin, one for the bone, one's focus, one's context, and so on. It's much livelier, in my opinion, when you can see it in action rather than just staring at static slides. And I know that some of you are wondering, is the copy of that video on the DataViz YouTube channel? And the answer is yes, if you want to have a look at it in your own time, because it's quite interesting. Any questions about the shear-warp factorization algorithm? It looks like an interesting test question, doesn't it? Or something like that. Looks like it could be the subject of a test question to me. Any questions about that one? Okay, good. I'm picking up a signal from the audience. Somebody's thinking, are there more volume visualization algorithms that we're going to cover, or what's next? Somebody's thinking that in the audience. Somebody's like, what's next? Is it going to be volume visualization, or is it going to be something new? So next Monday, we are going to switch topics again and start flow visualization. So that is basically the end-ish of the volume visualization part of the module. Remember, we had these three parts: InfoViz, VolViz, and then the third part is FlowViz. This is just a preview, right? What is flow visualization? We're going to talk about that. Different sub-classifications inside FlowViz, where FlowViz data comes from, a little bit about computational fluid dynamics, simulation versus reality, and some other things, dimensionality, and so on. A little preview. Okay, any other questions, comments? I'm having trouble keeping up with all the feedback from the audience. If there are no questions or comments, we will stop for today.